Is that fine? Can you hear me? Um,
Okay, our next speaker is Sylvain Lacroix, talking about integrable structures of the SG2 Wezumino with the Novikov model.
Thank you for the introduction. So thanks. Let me start by thanking the organizers for setting up this very nice conference and for giving me the opportunity to talk here today. And so what I would like to present is some joint work with Adrien Moline, who is also in the audience, and which is about the integrable structure of the SU2 Wezumino-Novikov-Witten model. And so to start with, let me give a little bit of introduction. And to explain the motivation of our work. And so the basic topic of my talk will be integrability in 1+1D quantum field theories. And there's several approaches to this. One often used is to try to bootstrap, for instance, the S matrix using integrability and so on. Here I want to come back to a more first principle, kind of old school basic notion of integrability, which is start by building an infinite number of concept commuting operators in my theory, which typically contain the Hamiltonian and the momentum as the first few charges, and then infinite tower of hidden symmetries, and then to diagonalize these charges on the Hilbert space of the QFT, which would give me then the exact spectrum and eigenstates. And this, of course, in general, is a difficult task. But what I want to present here is some preliminary results and conjectures on a specific example, which is the SU2 Wezumino-Novikov-Witten model. And so my plan will be the following. I will start by reviewing what is this theory exactly, and in particular the kind of algebraic aspects that I'll need. Then I'll talk about the integrable structures, so the construction of these commuting charges in that model. And then I'll talk about the diagonalization, and in particular, a rephrasing of the spectrum in terms of what is called the ODIM correspondence. But let me start then by a brief review of what this theory is. So to fix the convention, I'll be working with 1+1D cylindrical spacetime with Minkowski signature. And in particular, my spatial coordinate x will be periodic with period 2 pi. And on this, I will define my SU2 Wezumino-Novikov-Witten model, which is a conformal sigma model whose target space is SU2. So in principle, I could write it, for instance, in terms of a Lagrangian with a field valued in SU2, but I won't use so much the Lagrangian formulation. I want to focus more on the operator formulation because what I'll be interested in is more the algebra here. And so in particular, the conformal symmetry has for consequence that is a decoupling of the chiralities. And so I get left-moving fields JA and right-moving field JA bar, which are called Kac-Moody currents. And in particular, they depend on this index A, which is from 1 to 3. And this, I think of it as being a SU2, a Lie algebra index. And mostly here, I'll focus on the left-moving sector in this talk. And the main important property here will be the algebra that these operators form. And so here I write the commutator of the current at different values of space variable. And we find this thing. And as usual in QFT, we have Dirac distribution or derivatives of the Dirac distribution. Here, epsilon is the completely symmetric, skew-symmetric tensor. So that's the structure constant of SU2. So we get essentially the SU2 commutation relation, but a field theoretic version with a Dirac distribution. And then we have what we call the central extension, which is proportional to delta prime. And where, what should I do? Sounds good, hopefully. Yeah. So we have the central extension proportional to delta prime and proportional to a number k, which is called the level. And that's the main parameter that define my theory here. And J bar then satisfies similar algebra, and then J and J bar, they commute because of the chirality decoupling. So to understand a bit what's hidden behind, what's hidden behind this commutator, it's useful to go to Fourier decomposition. So because I work on the cylinder here, I can introduce the Fourier modes JAN, which really I'll be thinking of them as my actual operators on my Hilbert space. And then I can translate this algebra here, this current algebra, into the algebra of the modes. And I find the following infinite dimensional Lie algebra called an affine Kac-Moody algebra, SU2 hat at level k. And so this, if I look at it, so if I focus on the zero mode first, these terms disappear, And what I get is just the standard finite SU2 algebra. But now I get an infinite dimensional extension of this, which include all these non-zero modes. And one thing that will be important for me for integrability is that in this theory, I can also build composite fields by also taking, say, products of the currents. And a typical example is the so-called stress energy tensor of the theory, which is built as follows. So I take essentially a quadratic combination of the current, which is sum d over a, so I contract with the Killing form, normalized by this 1 over k plus 2 by convention. And what I mean by when we do this is essentially, if I want to do the Fourier decomposition of this new field Ln, well, I just insert the decomposition of Ja, and I get this infinite sum of product of J. And there's one subtlety, which is this double dot here. It means normal ordering. And what I mean by that is, well, if my Ja here has negative modes, I'll put them on the left, because later on we will interpret them as creation operator, whereas the positive modes will interpret them as annihilation operator, and so I put them on the right, and then this infinite sum will be well defined. And there's another slight subtlety, which is when I do this reordering, in fact, in general, I can have some kind of additional term that comes, in particular, some kind of finite size correction. They play an important role in some of the computation, but in my talk, they won't be too important. If you're curious about how it works concretely, you can ask me after the talk. But in the present case, what it does is very simple. It just shifts the zero mode. It just add a constant proportional to the central charge of the theory, which looks like that in terms of the level k. And in particular, now from the Kex-Moody algebra of the J, I can write the algebra of my new modes Virasoro, Ln, and I find the Virasoro algebra, which is the standard algebra of 2D conformal symmetries. And more generally, I could build more complicated fields than just JJ. I can take normal ordered product of more currents and so on. Okay, so that was kind of the main review of this theory, and now I want really to get to the new stuff, which is talk about the integrable structure of this model. So what I'll want to do in particular is then build some infinite tower of commuting charges. And here I'll focus only on local charges, by which I mean it will be like integral of a spatial variable of some density W. And this density W, I will construct it by taking normal ordered product of the currents and their derivatives, right? And in principle, because I know the algebra of the current here, then I can compute the commutator of all of these densities. If you want to know how this is done in practice, again, you can ask me. And then I can compute the commutator of the integral. And in general, this commutator will be non-zero, but now the main question is, well, can we find very fine-tuned choices of these densities such that these integrals commute one way or another? And here, the conjecture is that indeed we can find an infinite tower like that. So the first of these charge is very simple, is the case where the density is simply the stress energy tensor, which means I'm looking at my light cone Hamiltonian here. And this, recall, T is just Jj, so this I can think of it as a quadratic charge, something of degree 2 in the current. And now the idea is that the other charges in my tower, they will be higher degree charges, so some higher spin integrals of motion in my theory. And in particular, we expect to get every even degree. So we'll have degree 2, 4, 6, 8, and so on. And so the first non-trivial one would be a quartic charge, and it looks like this. So it starts with a T squared normal ordered. So that's something of degree 4 in the current. And then there's an actual correction by dja. So this is still of spin 4 because d is a spin 1 itself. And then the higher charges, they will start with t to the power p. So this is something of power of degree 2p, plus corrections involving also the derivatives of the field. And these corrections, they have to be extremely fine-tuned to ensure the commutativity here. They're essentially almost uniquely fixed by this property. So far I presented things in terms of densities, but I can also then write everything in terms of modes to really think of what is the operator I'm looking at. So for instance, for Q1, if there's the integral of t, so what I do is I just pick the zero mode here, which I recall was this expression here, normal ordered expression in terms of the Kex-Moody modes. And then I can go on and compute also the mode expression for the QP, the higher ones. And for instance, the quartic charge, it looks like this. The details do not really matter. This is just the result of doing the normal ordered product with also finite size corrections and so on. And in particular, all these QP, they should commute as a consequence of the algebra of these Kac-Moody modes. And let me mention, they also commute, in fact, with non-local charges that come more from a monodromy matrix, which are called Kondo defects, and which were studied by Benoit Vicedo, Davide Gaiotto, and collaborators in this paper. But here I'll focus only on the local part. Okay, so now that I have these commuting charges, I can ask about the diagonalization. And for that, yeah.
Your normal ordering prescription, is it the same as from the classic work that applies Houghton's document?
Yeah. This is the same. And the only subtlety is we're working on a cylinder, so we have to be careful about this thing. But I mean, the way I could do it is I do to the plane, I do the standard normal ordering, and then I change back to the cylinder, and that creates this finite size corrections. Yeah. So to be able to talk about diagonalization, I first need to say what's my Hilbert space. And here again, I'm guided by algebra, because my Hilbert space, well, it better be built from representations of my affine algebra here. But to go gently here, to give a bit of an introduction, I won't start with the representation of the affine algebra. I'll first focus with the finite case. So which means I focus first on the zero modes. And this is very standard SU2 representation. I introduce the raising and lowering operator, and then I can introduce the representation called a Verma module, which is a highest weight representation. So it have a reference state L, it's killed by the raising operator, and it's an eigenstate of the Cartan operator, J3, with eigenvalue L, which is what we call the isospin, so it's the quantum number of my internal SU2 symmetry. And then I get all the other states in the representation by acting with the lowering operator G0 minus, and that gives me new states with lower isospin. So that's standard SU2. Now we want to do the affine case. So we want to build an affine Verma module. And essentially what I need to do now is I need to explain what I do with my non-zero Fourier modes, right? And here the point is that the positive modes, I'll interpret them as raising operators. So in particular, they will kill the highest weight state here. And the negative modes, I will use them as lowering operators. And concretely, it means that all the other states in my representation, I can build them by acting with these two lowering operators. So F1 is J0 minus, so that's just the lowering operator in the finite SU2 direction. And then I add a new one, which I call F0, which is J plus minus 1. And it turns out that every other negative mode, I can build it as a commutator as commutators of these ones. And so then I get my new states by acting with a bunch of these F, but I have now way more possibilities than in a finite case, right? Because I can do F0, F1, 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 F0, I have a lot of different combinations. And an important remark is that if I take a normal ordered operator, like say my QP here, so these have infinite sums, but recall that I've put the positive modes on the right, and here the positive modes, there's the raising operator. So what will happen is that these infinite sums, in fact, they will always truncate because we will always kind of reach the highest weight, and then at that point, my sum will truncate. And so in particular, this type of normal ordered operator, they're well defined on the Hilbert space. So concretely, what that means is that I get then these QP, which are well-defined operators, commuting operators on my representation, so I can ask about diagonalization. And there's one which is very simple to diagonalize, it's just the light code Hamiltonian Q1. And it turns out that these states obtained by lowering operator, they're on the nose already eigenstates of this operator with the following eigenvalue. So this part here is the eigenvalue of the reference state L. And then what happens is every time I act with the F0, I shift the energy by 1. Right? And that then essentially gives me completely the energy spectrum of the theory. And I see that in this spectrum, I have a rather large degeneracy because like for a given En, there are many different states that have the same N because it's just the number of time I apply F0, but then I could apply a bunch of different F1 as well. So far, this was no integrability, kind of pure CFT computation, but now I can bring the integrability on, which is that on top of this Q1, I have also the higher degree QP. And they commute with Q1, so they should stabilize the eigenspaces of a given energy. But what's important is that there will be some non-trivial mixing. So these simple states here, they will not be eigenstates of the QP. in general, the QP, they will mix non-trivially these different states. And so in particular, the question of diagonalization is rather non-trivial. And we expect that in particular, this QP, they lift the degeneracy of Q1. They will have simple spectrum when I take all these QP. But even though this is non-trivial, it turns out there's a conjecture for how to diagonalize this, which goes under the name of the affine Bethe-ansatz, and which is what I'd like to present now. So this Bethe-ansatz, it goes as follows. So I take a number of Bethe roots, which are points in a complex plane, and then I attach to these colors, which are just either 0 or 1. And I build a Bethe vector by starting with my reference weight, and I act with my lowering operator, F0 and F1, where the 0 and 1 are chosen as my colors that I attach to my Bethe roots. And this here, recall that the ordering is important. And what I do is I'll sum over all possible permutations of this ordering. So if I do F0, F1, I will also have F1, F0. And I put also some coefficient in front of this lowering that are rational functions of my parameters W. The details do not really matter, but this gives me like an explicit form for one state inside of my representation. And here the main conjecture is that this will be an eigenvector of my QP if and only if the Wi satisfies some algebraic relation called the affine Bethe-ansatz equation, which looks like this here. And so that gives me then a nice quantization condition for this theory. And this, we checked it in explicit low-lying examples. So for the first few charges and a few number of excitation of lowering operators, and it always worked well. And we conjecture that it's complete so that we can get all the eigenstate this way, at least for like generic values of the parameters. Yeah.
So is this on the previous slide you said there were many states with the same energy. Now, is what you're doing here, you're constructing a basis for those degenerate states, but states that all have the same energy.
Yeah, so this essentially, so if you here, there's the same number of F0 in each of them because it's just fixed by the colors I have. So it's fixed by the number of 0 colors that I have inside of my Bethe roots. So they all have the same energy with respect to Q1. But now essentially it picks up a very specific basis inside of there that will be an eigenstate of the higher QP as well. Right? And what we expect, in fact, is that it turns out Q3 seems to be enough to already completely split the lift of all the degeneracy. Okay, so this gave me the eigenvectors, well, at least conjecturally, but so far I didn't say anything about the eigenvalues. But fortunately, there's another very powerful conjecture, which gives us all the eigenvalue through inside of what is called the ODIM correspondence, and which here, the way we find it is by using Langland's duality. So I won't talk about the Langland's duality, I will just want to explain what's the concrete consequence in the end for this in terms of this ODIM correspondence. And in fact, we'll hear about the ODIM correspondence later on also in Thomas' talk, but I think for another model. So this correspondence, on one side, I have ordinary differential equations, and on the other side, integrable model. So this side, I just presented it, is this Wezumino-Witten theory with some commuting QP. So now I need to explain, well, what's on this ODE side. So for this, I'll look at specific type of ODEs, which depend on a complex variable Z. And here I want to insist this has nothing to do with the spatial T and X that I had initially. It's some auxiliary complex variable, some kind of spectral parameter if you want. And I'll look at linear ODEs of second order. So essentially they will be Schrödinger type ODEs like this with some potential. And slight subtleties, I will also allow for quantum correction to the potential, something of order h bar squared in the potential. And let me say here, I use the name h bar because this would be really the Planck constant for my Schrödinger equation. But this h bar has nothing to do with the h bar of my actual QFT, my Wezumino-Witten theory. Again, it's some kind of formal auxiliary parameter. And the kind of object I'll be mostly interested in associated to this ODE is some monodromy. So if I take a contour gamma, closed contour gamma, if this contour encloses some poles or branch cuts of my potential, in general, I can have monodromy around these. And these monodromies, they're encoded in some object called the Voros symbol or the quantum periods. I won't go into all the details of how these are defined, but they essentially encode the eigenvalue of the monodromy, if you want. And what will be important for me is that these have a semi-classical expansion in h bar for the so-called WKB expansion. And so this starts as a 1 over h bar term, and then there are a power series in odd powers of h bar. And what is nice is that there's an actual formula on how to compute this. There will always be integrals of some specific combinations of u and v, and there's some kind of recursion relation on how to find the integrand here that I need to look at. And that's the kind of tools I will need to use. So to make the link between my ODEs side and my WZNW side, I need to choose specific choices of ODEs. So I'll essentially fix the potential VZ here to be always the same. It's ZK exponential minus Z, where K is the WZNW level. So in particular, my WZNW parameter now enters my choice of V. And for those who knows this word, this is very related to the twist function. This thing is such that its logarithmic derivative should be the twist function of the theory. So essentially the omega in Fordich and Simons, if you want. And I also fixed the contour gamma on which I'll compute monodromies to be this Henkel contour. And essentially what that does, it goes around a branch cuts here. And the last thing I need to do is this U, I will need to choose it to be in correspondence with my Bethe vectors. So to each Bethe vector I need with Wi and color Ci, I introduce this object here and compute what is called its Murat transform, and that defines for me my U. So just to finish, to wrap up, essentially I have a correspondence between some ODs and some Bethe vectors. And then the ODIM correspondence will tell me two things. The first one is a fact, it's proven, is that although this has pole at Wi, it could have monodromy, but the claim is that there's no monodromy around Wi if and only if the Wi satisfies the Bethe equation. So that's the first link between the ODE and the integrable model. We recover the quantization condition by this no monodromy condition. And the second, it's conjectural, is that the spectrum of QP, the eigenvalue, they're extracted in the WKB expansion of this monodromy here as this coefficient with some proportionality factor here. This, we know it explicitly, is some ratio of gamma function in terms of the level, and it's independent of the choice of the states. It's just kind of a universal factor. And this, again, we checked this conjecture for the first few charges and the first few states, and it works well. So I think I'm getting low on time. So just for conclusion, to just briefly say the word, we can also go to higher rank. There's also multi-currentializations or cosets thereof. And what's nice is there are always conjectures also for Bethe-Ansatz and ODIM for all these theories. But I think the most interesting generalization would be to go, this was at the CFT point, and we would look also like at massive deformations like JJ bar deformation. And it would be nice if we could also transfer the integrable structure to this massive theory. And with that, I'll stop and thank you for your attention and leave the conclusion, maybe, if you want.
Thank you very much for the nice talk. Questions?
A couple of questions. So one is if you have thought about what could happen for SL2R, and the other, if you do a marginal JJ bar deformation, is it obvious what it happens, or do you know it already?
Yeah. Okay. So these are good questions. So about the first one for SL2R, so here I essentially just used the algebra kind of complexified, and I didn't put any condition on my level K. It could be a non-integer and so on. So I think everything will work the same, at least algebraically. Then of course the representation is harder. And then depending on the type of representation, if it's still highest weight, then we can say something. If there's no highest weight, then it's not obvious at all how to diagonalize these things. And in particular, this could be interesting, for instance, in application to ADS3 and so on. But then it's not obvious what to do in that case. For the second question, you said marginal JJ bar. So I guess that would be the JJ bar if I do only in the Cartan direction, for instance. Yeah. So this, supposedly, I think this should give some kind of anisotropic version of this, where I kind of break the, here in my QP, they had a SU2 symmetry. Here I probably would break it to U1. We haven't looked at this, but probably there exists a deformation of the integrable structure adapted to that as well.
Hi. So much of this construction looks like it's related to the existence of the Kac-Moody algebra of the WZW. If you go away from the CFT point, in general, you don't have that enormous amount of symmetry. So how could this still work?
That's a very good question. So it's true that when you do then, for instance, JJ bar, the non-abelian, like the full JJ bar, which would be not marginally relevant, you might lose a lot of the symmetry you have in a CFT. You don't have all this technology of Carl vertex operator algebra to work with. And then it's not completely clear what to do. Probably one good option would be to try to do things like what Benoit and Ricky did in try to renormalize some operators and try to define them and show that they're still there along the flow and that they still commute. But probably it's very hard. The main answer that I can give now is we have no clue, I think, of concretely what to do. Although maybe one thing is to at least do conformal perturbation theory. So like in the first order in the lambda times JJ bar, maybe we can do some stuff and still get things. But like a full rigorous construction here seems hard at the moment. Yeah.
If I may add, I think there is hope in the case of deformation in the full group. If you take K large, so you expand.
Yeah, I guess for K large you also.
For K large, I was saying, if you have a deformation JJ, but not in the Cartan, but in the full group, you can set up a perturbation theory for large levels for any lambda, but for large levels.
Which I guess would be a semi-classical.
Semi-classical
Yeah.
approach.
Yeah.
Why do you call Q1 a light cone Hamiltonian?
So here I just took the integral of t, but then there's also there's the right moving sector that leaves its independent life, and I also have a Q1 bar, which is the integral of t bar, and these would be my two light cone Hamiltonian, right? One generate the d plus derivative, the other generate the d minus derivative.
Can you get an S matrix in this way?
So here, the thing is I'm at the CFT point, so I don't have like massive excitation that scatters.
For massless excitation.
That's a good question. The answer is I don't know.
If not S, how about R?
Sorry?
Do you do R matrix?
So, well, I mean, in some sense, everything here is based on some kind of R matrix, like some kind of quantum Maillet bracket, but in a very simple way here. But this generalization that I mentioned here, which are based with like multicurrent, they're essentially based on an object that satisfies some kind of quantum Maillet bracket. But where there's an R matrix behind, but the construction of the charges themselves doesn't go at all to all the RTT formulation and the standard Yang-Baxter formulation. And it's kind of there's all the problem of non-neutral locality and so on that tells us it's not obvious how to do RTT in that case.
Sorry, maybe I have a question. Maybe you said that, but could you just remind why at all do we expect to have this set of infinite charges and all this integrability?
Why do we expect that it's the case?
Are there some general arguments that they should?
Yeah, so I think mostly what we know is we know them at the classical level. So at the classical level, for instance, there was the lambda deformation that Kostas looked at. And then we have a lax pair, for instance. And so we have a lax connection, so we know this classical integrability. And in particular, you can take the UV limit of this thing, which will go to the Vesuminov-Witten theory. And if you follow what happened, essentially the integrable structure will decouple into a left moving part and a right moving part. And then there are some non-local charges, which will be the Kondo defects that people have looked at. And then there's also some local charges, and they look like what I presented, but at a classical level. And there we know them. And now the main question is, well, can we find them also at a quantum level? That was classical. And now we ask about, well, can I quantize them? Can I find a choice of ordering and so on that makes it still commute?
And why this quantum structure should exist?
Well, I guess maybe very generally, there's this story about affine Godin model where we expect that there's a very general class of quantum model based on affine algebras that have an integrable structure, and the existence here is related to some kind of generalization of the geometric long-Lens correspondence. that doesn't say much concretely, but I think it's just, I mean, yeah, it's a bunch of things that we know are classically integrable and that we have good reason to think that for some of them, for instance, we are able to write an S matrix. For the massive theory, we're able to write an S matrix that seems consistent. So it seems reasonable that we should have a construction, like an integrable first principle construction, at least at the UV fixed point, for instance. And for the lambda model, that's the case. So.
May I ask also one question? These charges that called Q with an index P, they seem to be powers of currents, correct?
Yeah, yeah.
Plus corrections with derivatives.
Yeah.
So that means they look like Casimirs in the Lie algebra, but for SU2, we don't have cubic Casimirs on our. So how it seems to be?
Yes. So if I look back, for instance, at my
Q2, but not higher.
Yeah. So essentially, the Q2 they will start the QP. They start with T to the power P, and this year the corresponding like invariant tensor that I have is just like P times the Killing form, right? And
yeah,
so,
but for SU2, DABC is 0.
Yeah, but it's not cubic, right? This then, for instance, this T squared, so this would be kappa AB, right, as the invariant tensor.
Quadratic, yes, but what about the cubic?
There's no cubic. Here we expect only even degrees, like degree 2, 4, 6, and so on.
So, but for degree 4, what would you put? Just deltas, Kronecker?
I think then we contract JA, JB, JC, JD with kappa AB, kappa CD.
These are independent ones.
Yeah, these are independent, like these are independent ones. So classically, the densities would not be independent, but once we take the integral, this then becomes independent objects, like in terms of modes.
More? Okay, let's thanks. Okay.
Now, sorry, we're delaying the photo.
Yeah, sorry. Just a super quick question. How much of this do you expect to be generalizable beyond SU2?
So we think that it should be there. Actually, we even have a conjecture for the Bethe-Ansatz and the ODIM for these cases as well. And what happened in that case is that the degree, the spins of these higher spin thing will be what I call the exponents of the affine algebra. So they follow a different pattern. This will not be like 2, 4, 6, 8, but they will be like a different pattern depending on the algebra. We don't know the explicit expressions, and it gets messy if you try to do it, but there's good reason to think that they exist. And at least for SL3, we know that there's a cubic that exists from some